same number of columns.
Where is it? What's the start and finish?
Start and finish. So the thing about Dijkstra's is it's actually not like you don't know like the finish really ahead of time. You're not specifically calculating the finish, like the path of one specific thing. Dijkstra's actually gives you the shortest path to every single node on the graph from one point. It gives you more information than you need, basically.
Yeah, but in our case, I guess like for the purposes of
yeah, we can start it.
For the purposes of our problem, you can choose like the start and the end.
Okay, sure. So
because that's how big.
Let's just say our start is A, and we can make the end H. Okay, so what do you think should go in the rest of these spaces right here? Anyone? Right here? Now X is infinities, right?
Why are they all infinities?
Infinity, they see in here is a symbol which represents you can't reach like any of these other nodes at this point. Like we don't know, the distance to like H right now is infinite. Like we're at A and we just can't reach H. We can't even reach B, C, we can't reach anything right now. So,
why can't you reach B, D, and C? They're directly connected to A.
So you can, and that's the next step. But basically, what each column is it represents like a slice of time in our knowledge right now. So the only thing we know right now for A, we don't know what this rest of the graph looks like. Like imagine you're standing at this point and you can't even see the rest of the graph. So you're just at A. All you see is A. You don't know there's B or D, any other paths. So this like slice in time of our knowledge, all we know is A, and we're at A. This is like kind of a redundant like step basically, but it just is useful. So maybe it doesn't have the most relevant information, but we'll see going forward. So the next step is to make another column. Now our knowledge expands a little bit. Now it's going to be time for an A, and we're going to look out and see what's connected to A. So what is A connected to? It's connected to a B, it can go to a D, and it can go to a C, right? So the path from A to B is 8. The path from A to D is 5. The path from A to C is 2. What's the path at this slice in time with our current knowledge? What's the path from A to F? That's right. Same with E, G, H. At this point in time, we can only see the nodes B, D, and C.
For A, exit out and put it in this place.
Joe, why did you put an X?
So the X right here, the X right here means we've visited this node. We've completed looking around at other nodes. And so we're not going to go back and visit that node again. So we don't need to consider it for the rest of the variable. All right, so now we choose the smallest distance out of our current column right here, right? So what would that be, 2? And we go to node C. So now we've already visited node A. I'm just gonna denote a check mark. Now we're at C. We can check this off because we're at C. Eventually we're gonna fill C with a bunch of X's. So we can actually just do that right now. So now that we're at C, our knowledge is like expanded. We can look and see what C is connected to. It's connected to A, we already visited A, so we're not gonna consider that. Now it's connected to D and E. We already looked at D, and we saw that the current path from A to D is 5, taking along this edge. But based on C, you can get to C in 2 steps, and you can get to C and D in 2 steps. So in total, you can get to D in 4 steps from A. That's shorter than 5. So what we're going to do now is change this to 4. And we're going to say we got to D from C. I'm gonna subscript it saying like we got to D from C there.
Can you subscript the other ones in the first
Yeah.
column?
Okay. Then what about E? E, we can get there in C, which is 2 plus 5, so that's 7. And that's all the nodes so far that we can see from C. So B, as far as we know right now, still takes 8 to get there. And F, as far as we know, we don't even know how to get there, same with G and H.
And so we added C to the set at the last step.
Right. So, can anyone tell me at this column, now that we have this knowledge, what's the next node that we're going to want to look at?
D.
Yes. Well, actually, yes, we're going to look at D. So we can check that off. And let's see. Now that we're at D, we'll look around. So we already went to A, so we don't need to look at that. We already visited C, we don't need to look at that. Let's look at E. You can get to E in the current value of D plus 1, so 5 steps. So we're going to update that to 5, we got there from D. So now let's look at G. G, the current value of D is 4, and we can get to G, 4 plus 3, so 7. And we got there from D. H, still can't reach H yet. F, the current value of D is 4 plus 6, so that's 10. Let's see, did I do that? Sorry. And now that we're looking at D, we can just exit it out. Everything. B, we can get to B from the current value of D, which is 4 plus 2, so that's 6. And we got there from D. So now let's add D to the set. Okay, what's the next node to look at?
Oh, E?
E, right?
So
Because
sorry.
it's the lowest number in it. So we're at E. Let's check this off. So we can't look at C because we already looked at it. We already looked at D. So now let's look at G. So the current path to E is of length 5. Plus 1 to get to G, so that's 6, which is shorter than our previous path to 7. So the current path to G is of length 6, and we just got there from node E. Okay, that's the only node that you can look at right now. So we're just gonna exit out the rest of E, and then just copy everything else over. What's the next node to look at? So our two smallest values are 6 and 6. So they're tied, so we can just choose which one we want to look at right now. So let's look at B.
Wait, don't you have to go to somewhere that's next to E though? Because you're at vertex E? Or is that not the case?
No.
It's not the case.
Okay.
So we're looking at B. B already checked out A. B's other neighbor is D. We already checked out D. We haven't fully checked out F yet. So the current value of B is 6. Plus 13 is 19. So that's the path through B to get to F would be of length 19. But that's way longer than our current path that we already know. So we're not going to update F. We're just going to copy over what its current path is. I'm going to X out B because we're visiting it right now. So that was B's only neighbor, valid neighbor that we can look at. So we'll just copy over the rest of everything. Alright, so now the smallest one in this list 6, which corresponds to G. So we'll put a check mark there. So G's neighbors are F, H, and E and D. D and E we already looked at, so let's check out its values to F and H. So the current value of G is 6, plus 2 to get to F would be 8. That is shorter than our current path to F. And we just got there from G, so I'll subscript it there. Finally, we can get to H. And the current value of G is 6, plus 6 to get to H is 12. And we got there from G. Okay. So now, does anyone want to tell me what the next node is? So looking at the smallest values in the table, which is F, we're right here. So F's neighbors are B, D, G, and H. H is the only one we're going to look at because B, D, and G have already been visited. So the current value of F is 8, plus 3 to get to H is 11. That path is shorter than our current path of 12, so we'll update that. And we just got there from F, so I'll subscript it. And we're looking at F, so I'm going to cross that out. So at this point, we should have enough information to determine the shortest path to H from A. Our whole table is filled out. Now, given this table, we know the shortest path from A to any other point on the graph. So to get from A to H, first we're going to start at H and work backward, all right? So this will be, what I'm writing right now will be the path from A to H. So we look at H's value, we see that the subscript is F, that means we got there from F. Then we look at F subscript, F's subscript is G, so that means we got there from G. So G, all right, where do we get from G from?
E.
Okay, and where do we get from E from?
D.
And then we got from D, we got to D from C, and we got to C from A. Right? Yeah, so that should be the shortest path.
With a delay of what?
So the total delay, let's add it up. So A to C is 2. C to D is 2. Well, actually, we don't even need that. We can just say it was 11 right there. Yeah.
So you don't need to check like when that time you have 2 links are the same, or just like, oh, choose this one.
Can you say that again?
Because there's one point like when we were counting that you said, oh, these 2 links are the same, so I'll just pick this one.
So in that case, that's okay to do, because what I was doing is I was just saying out of the 2 shortest values, let's just pick this one to check and follow and see what its nodes are. There could possibly be a case where, so basically this is like a unique path. There's only one shortest path. However, it's possible to have 2 paths which are the shortest path. Something in that case, what it would look like is, you know, when I was updating the values and I said like, okay, we found a way to get to F and it's only length 11, so that's shorter than G. But what if this was, let's see, if this was 4, then this means this would be 12. And then we'd also, since this is not necessarily shorter than this, we'd also have to include this in our final answer. So that way, what this means is the length to get from A to H is 12. We can go from H, and then instead of this being F, this could have been G, and then maybe we would have followed the path back to A, but we started from G and not necessarily from F. So that's the case where there would be 2 different paths.
Yeah.
Yeah.
But there's no way the other path would be shorter, or is there like?
What do you mean by that?
No,
We
so-
like other.
So it is, so the example he just gave, and also the example we saw earlier in the middle of the table where we had to choose between B or E, I think, because it was a tie. That means that like, there were possibly like two shorter paths, not just one. So you can like, when you find a tie, you can choose one and just go on with that path, or you can find another table and do like both, and you would find like maybe two shorter paths.
Okay, so it's just your choice.
Yeah,